Alright guys, today we're going to talk about section 12.2, which is transforming to achieve linearity. Alright, so even though this is not a big part of the AP test usually, it is still on the AP test in some manner. Alright, so sometimes when we look at data, alright, the data might appear linear. Like for instance, I put some numbers into a couple lists, and then I just made a scatter plot of it. So if I'm looking at that scatter plot, I might believe that that data is linear. Okay? So the only way to really check that, okay, because that data does look linear, the only way to really check that is to go through the regression. So do a linear regression on that. So quit out, go stat calc, number 8, linear regression. My data's in list 1 and list 2, and I can store the regression equation in y1. I can calculate it. It'll give me the numbers, and if I hit graph again, it will put that line in there. Okay, the line's fairly close to the points. However, you might see a possible issue here. Look at that point and that point. Both of those points are beneath the prediction line. Then the next 1, 2, 3, 4, 5, 6 points are above. And the next 2 points are below. Okay, so this shows some sort of pattern. Let me turn that line off real quick. And now, instead of looking at the scatter plot, let's look at the residual plot. So we choose the first option. Oops. All right. Now, instead of looking at L1 versus L2, we're going to look at the X values versus the residuals. Okay, now when you calculate regression, the last regression you did, the residuals are automatically stored. Okay. And if you actually want to see the numbers as the residuals, I could go under one of my lists and I can actually display the residuals if I want to. Okay, so I can go up where it says L3 and put the residual list up there. It'll say L3 equals list resid, or L resid. Okay, so it looks like I have residuals of -4, -12, -4, +2, 6, +8, +8, +6, +2, -4, and then -12 again. Okay. So if I actually wanted to plot those, there's 2 ways to do it. I could do L1 versus L3 or simply L1 against that same residual. Okay. And then zoom 9 that. All right. So what we want to happen is we want this residual plot to be randomly scattered. Looking at this residual plot, there is a clear pattern to it. Okay, there's a clear quadratic pattern to it actually. This is not random scatter. So what does that mean about the original scatter plot? Okay, let me go back to the original scatter plot here. L1 versus L2. Zoom 9. That was the original scatter plot. The data looked like they were linear, but it's really not when I examined the residual plot. So when that type of thing happens, we always need to check the residual plot for random scatter. If it's not there, we have to do special things. Okay. And what this first page tells you is what to do if your residual plot shows a pattern, if it shows some sort of type of curvature. Okay. The first thing we're going to do, all right, look at question 2. How do I transform? Simple answer is guess and check, but you must apply some type of non-linear pattern to the X data, the Y data, or both. So what these 3 steps essentially do, and you can read this on your own, okay, we can do the X list against an ln of the Y list. If that still doesn't work, we can do the ln of X versus the ln of Y. And if that doesn't work, we can just do the ln of X versus Y. So if you do these in these steps, you'll usually get something that eventually the residual plot is not curved anymore. So let's try it with our data. Okay, let's go under, all right, let's go stat, edit. Okay, let me get rid of list 3 because that was just the residuals from before. All right, I'm going to zoom in a little bit. All right, so the next thing I'm going to try, I want to have my x values in list 1 against the natural log of stuff in list 2. So I can let my calculator do this for me, just up where it says L3. I can just hit the LN button, and the calculator is saying you want to take the natural logs of what? I want to take the natural logs of all my y values, which are in list 2. I hit enter, and now I get the natural logs of all these numbers. So the natural log of 20 is 2.9957. Now we can make a scatter plot of list 1 versus list 3. So let me go back in here. So we'll make a scatter plot of list 1 versus list 3. Zoom 9 it. Okay, I can tell right away that's not going to work because look at that pattern. Definitely not linear. So that's not going to work. Okay. All right. So what can I do over here? Well, let me just delete list 3 here. And now I can take the ln's of both of these things. So I'm just going to skip list 3 for the time being. So I can take an L4, I can take the natural logs of my x values, which are in list 1. And I'm just going to do this again. All right, I'm going to take the natural log of my y values in list 2. This is the same thing that was in list 3. And now I can try to plot these things against each other, L4 and L5. Okay. I'm going to go under my scatter plot, and I just want to look at the scatter plot of L4 versus L5. And zoom 9 it. Okay, that one looks a little bit better. If I did regression on this, okay, I'd be using L4 and L5. I can store my equation in Y1. And if I graph, that's a little bit better, but it's still a little bit, shows a little bit of curvature. Okay, let's look at the residual plot of that one. Okay. So I'm going to turn the line off. I'm going back under my stat plot. Now I'm going to do L4 against the residuals that were just automatically calculated for me. And zoom 9 it. All right, not so good. I thought it was good. It's not that good. All right, so there's one more thing to look at here. All right. The last thing I can do is I can look at the ln of x's, which are in list 4, against the original y values in list 2. All right, so let's look at that. Okay, so I'm going to do L4 against L2 and zoom 9 it. Okay, let's take a look at let's run the regression. And this one's going to be L4 versus L2. Store it in Y1 again. And you can store it in other things than Y1. You can put them in any one. Okay, and calculate it. I can graph. I'm going to put my line in there. Shows a little bit of a pattern, it looks like. Let's turn that off real quick. And now let's look at the residual plot for that. I'll be looking at L4 against residual. Zoom 9. Okay, there's a pattern there too. Okay, so none of these are that great of options. And none of them are that great. They all show some sort of type of curvature pattern. And that's probably just because of the data I put in there. Okay, it's probably because of the data I put in there. So I'm going to switch up my data real quick. Let's get rid of all my data. I'm going to clear my lists. Okay, so we can do this together. All right, so just pick some numbers here. So I'm just going to pick 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I'm just going to type in some numbers here. All right, maybe 11.2. I don't know, 21.6. 34, 41, 50, 58.3, 68, 74, no, that's too low. About 76.8, 85, and 94.3. Okay, so just put that data in. And let's just look at a original scatter plot of L1 versus L2. Zoom 9. Okay, so when I first look at it, it looks pretty good. It looks pretty linear. So let's run regression on it. Okay. So L1 versus L2, store in Y1. Calculate. Okay, it's going to put the graph in there. Line it. Okay, it's going to put that regression line in it. Okay. But now, if we turn that line off, and we change the plot, instead of a scatter plot, I look at residuals, and zoom 9 it. Okay, that one's not, that's not really random scatter so much. Okay, kind of shows a pattern a little bit. Okay, these two are clearly below. We don't have below and above. Then I get a whole series of things that are above. Then I get something really close to the line. Then I get something above. Okay, so most of this data is above. I get 2 more points that are below. This really isn't random scatter. All right, so if we follow the steps there, okay, the steps that we had before, all right, let me go back under my list. All right, now I want to take the natural log of the y values. Okay, so maybe let's just put those in L4. Okay, so natural log of the y values, which are in L2. Okay. Now if I look at a scatter plot, okay, we'll have L1 versus L4. This is just going to be the scatter plot. Zoom 9 it. All right, that didn't make it look better. That made it look worse. Okay, that's curved. That's clearly curved. So it's not going to be linear. Scatter plot's going to look even worse than it did. Okay, so the next thing we would try, we would go back into our list. Okay, and I want to look at the ln of x, so the ln of these numbers against the ln of these numbers. So you take the ln of list 1 now. Okay, now let's plot L3 versus L4. And zoom 9 it, zoom stat it. All right, that one looks pretty good. It looks better than the original. All right, so if I run the regression here, stat calculate number 8. Okay, so let's look at L3 versus L4, the regression. Okay, we're doing that to get the residual stored in our calculator, by the way. If I graph, it's going to put the line on there. Most of those are lining up pretty much right on the points, which is fantastic. Okay, so it's looking more linear than it has. All right, then if we look at turn the line off and look at the residual plot of that, so we'd be doing L3 against residuals. And then zoom 9 that. Okay. Still a little bit of a pattern, but it's better. Okay, this looks like more random scatter. It looks like maybe one outlier that's really high. Okay, one outlier that's really high. But it looked better than the original. Okay. The last thing that we just might want to check out, which residual plot gives the most random scatter. So the last thing we would look at, okay, under our list, we could just look at the ln of x, which is in ln of x, which is in list 3, against the actual y values in list 2. So L3 versus L2. Okay, that shows that's pretty clearly curved. Okay, so the step 2 looked like the best option. So that's the process that you have to go through if you're given data. Okay, now whatever question you're given on the AP test, it's going to become pretty apparent which one is best. So let's go through this example to help you understand a little bit more. It says, one sad fact about life is that we'll all die someday. Many adults plan ahead for their eventual passing by purchasing life insurance. Many different types of life insurance policies are available. Some provide coverage throughout an individual's life, which is called whole life insurance, while others last only for a specified number of years, which is called term life policies. The policyholder makes regular payments, which are called premiums, to the insurance company in return for the coverage. When the insured person dies, or if they die within that term amount of time, a payment is made to designated family members or other beneficiaries. It says, how do insurance companies decide how much to charge? They rely on a staff of highly trained actuaries, okay, which is a great career to go into, by the way. It's people with expertise in probability, stats, and advanced mathematics to establish the premium rates. For an individual who wants to buy life insurance, the premium will depend on the type and the amount of policy, as well as on personal characteristics like age, sex, and health status. For example, if someone's a smoker versus a non-smoker. The table shows monthly premiums for a 10-year term life insurance policy worth $1 million. So if someone who's 40 buys a 10-year term policy, it's going to cost them $29 a month. Okay. As you can see, as you get older, there's probably a higher probability of dying, and that's why the premiums go up. That's what these people, they set rates. Okay. It says, on your calculator, make a scatter plot of age and your X value, or your X list, and monthly premium as the Y list. And it says, describe the relationship you see. So let's go ahead and go in here. Okay, let's clear the list real quick. Quick way to clear a list. I go second and I hit the plus sign. That's going to get me into my memory menu. Go down to option 4, clear all lists. Hit enter, and the list will be cleared for you. Okay. So list 1, I'm going to put my X values or my ages. Okay, so 40, 45, 50, 55, 60, and 65. And on list 2, I'm going to put my Y values or my premiums. 29, 46, 68, 106, 157, and 257. And we're going to make a scatter plot and look at that data. It's just going to be list 1 against list 2. Zoom 9. Okay. So on first inspection, you might say, well, there's a positive relationship. As age goes up, premium goes up. Kind of looks like there might be a little bit of curve to it. Okay, so the data might not be linear. Okay, so I would say it looks kind of linear in the scatter plot. Okay. It says, run a linear regression and record the equation of the least squares regression line, the correlation coefficient, and the coefficient of determination. Okay, so let's run regression on this. So I'm going to quit out of there. I'm going to go stat, go over to calculate, and linear regression is option 8. That's the one we like to use. We don't like to use option 4. Okay. My data is in list 1. Oops. We're going to use list 1 and list 2, and we're going to store our regression equation in Y1. Okay. So it's telling me I need to record this. So it says y equals a plus bx. A is the y-intercept, b is the slope. Okay. So to me, this looks like the expected premium, or the expected y value, these are y's, these are x's, equals, according to my calculator, negative 342.8, all right, plus 8.6343, if I round up 4 places, times the x value, which is h. Okay, so that's my prediction equation. Okay. My correlation, R, is 0.9485, which we would consider very strong if the data really is linear. Okay, and the coefficient of determination, r squared, if we were to square that r, we would get 0.8997 if I round. Now make a residual plot on your calculator and describe what you see. Okay, so I ran the regression. You got to run the regression before you make a residual plot. Okay. So now I can do the residual plot. I'm going to go L1 against the residuals that are automatically stored in the calculator. Then I'm going to zoom 9 that, but before I zoom 9 it, I'm just going to turn off that line. Okay, that kind of looks like a curved pattern. Okay. This looks like a curved pattern. So I would say, I'd make a sketch of it. Okay, so this would be the residual plot. Sketch. Okay. Data appears to have a pattern. Or I should say residual data appears to have a pattern, therefore not appropriate to use linear regression. Okay. The residual data shows a pattern, which we don't like to see. If this was random scatter, that would be great, and I could trust in these things. So these things, it doesn't matter anymore. Now, number 2, it says on your calculator, make a scatter plot of age versus the natural log of the monthly premium. Okay. So I'm going to go back under my list, and then L3 here, actually I'll put it in L4. I'm going to take the natural log of the y values in list 2. So natural log of list 2, hit enter. Now I'm going to graph these things against each other, the x values versus the ln of y's. Okay. So I'm going to go back under my stat plots, and I'm going to look at L1 versus L4, just for the scatter plot. I'm going to zoom 9 in. Okay, that looks kind of linear. That's good. Okay, so when I do the when I do age as the x variable versus the ln of y, or the ln of the premium as the y, all right, scatter plot looks more linear than it did before. Than in number 1. It tells me to run a linear regression and record the equation again of the least squares regression, the correlation coefficient, and the coefficient of determination. So we're going to do the same thing we did before. We're going to run regression on that. So stat calc number 8. All right, I'm going to do L1 versus L4. This time I'm going to store the equation in Y2. Calculate. I'm going to graph to see that line. Okay, looks like it's pretty much going through every point, which is awesome. Okay. Let's just run that again, stat calc 8. I forgot to record it. Okay, so this equation would be predicted premium equals, actually, it's the natural log of predicted premium. Sorry, I forgot about that. Because it's the ln of y, so the natural log of predicted premium equals negative 0.063326 plus 0.085918 times the x, which is the age. I'm getting that from this calculator right here. Okay. The R has gone up to 0.9996 if I round, and the R squared has gone up to 0.9991. Okay, so not only does the data look better, look more linear after I did that transformation, I'm actually getting a higher R value and a higher R squared value. Okay, but we do have to look at the residual plot to make sure it doesn't have a pattern. Okay. So how am I going to look at the residual plot? Okay. I'm going to turn that Y value off. Go back under my stat plots. Okay. Now I want to look at the X values, L1, against the residuals, which is at the very bottom. Zoom 9. Okay. No clear, distinct pattern here. Okay, some are below, some are above. It kind of happens randomly. Whether they're above or below, there's no pattern. So in this one, the residual plot shows no pattern. And that's what we want. So this worked for us. The X value versus the ln of Y. And that's what we're really trying to do. Okay. We want things to be linear, so our linear regression works the best. Okay. This was not linear, so everything we did here doesn't matter. We can't use that. The residual plot has to have a random scatter. And a sketch of that residual plot. Okay. That's what the residual plot looked like. So something close to it, above, below, above, below, below, and above, something like that. So here's the residual sketch of residual plot. And that last question. Okay, now just as a matter of finishing this out, see which one works the best. Okay, let's go back under our list here. And now, so this was original X, original Y. Here's the ln of Y. So let's just look at the ln of X's. So natural log of the data in list 1, I'll put that in list 3. Then I can look at a scatter plot of L3 versus L4. Zoom 9 it. Okay, that also looks linear. I can run a regression on that. That is in list 3 and list 4. I can store that one in Y3. And we'll write that down. So the way I would write down this regression line, they're both ln's. So ln of predicted premium equals, and the equation from the calculator is negative 12.9834 plus 4.415, but we're not using, sorry, 4.4159 times the, we're not using just x now, we're using the ln of the x variable, which is age. So when you use ln, you got to use that in the formula as well. And then the calculator tells me that the R value is 0.99647, and the R squared is 0.9930. So not quite as good R value or R square value. They're both very high, don't get me wrong. They're both very, very high. But it was a little bit better on the last one. Okay, here's the last one. Okay, here we have 0.9996, 0.9991. Okay. even better in that one. But let's look at the residual plot now that we ran the regression. We'll turn that third equation off so we don't see the line. Go back under my stat plot, and I'll be looking at L3 against the residuals. That'll make the residual plot. All right, this one I wouldn't use it because the residual plot here shows pattern. Okay, it shows a pattern. So I wouldn't use that one. We'll say residual plot shows a pattern. Shows a curved pattern. So that's what it looked like. So it'd be not appropriate to use linear regression of ln of x versus ln of y. The second one, when you get one that works, you can usually stop there. All right, when you get one that works, stop there. So it wasn't really necessary that we did problem 3. Number 2 was good. We could have stopped at number 2. All right. Example 8, it says, consider the regression equation. The natural log of predicted transistors equals 7.0647 plus yada 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 times the year since 1970. It says, what is the predicted number of transistors for the year 1980? Okay, so let's just go through the algebra here. So we're trying to find that predicted transistors, so 7.0647 plus 0.36583. Now in 1980, how many years would it have been since 1970? Well, if we subtract these, it would just be 10. Okay, so let's go ahead and figure out what the right side is here, just by using our good old handy calculator here. So 7.0647 plus 0.36583 times 10. Or 10.723. But that is not your answer. What you have to do is you have to know how to manipulate that. We're trying to solve for this. Okay, so how do we get rid of ln? We got to put an e there because we know e cancels out ln. So predicted transistors is actually e raised to that power. It's e raised to that power. So the predicted number of transistors is 45,387.86239. That is the answer. Part B. It says in 1980, the actual number of transistors produced was this amount. Find the residual of this data point. Okay, so what do we know about residuals? Residual is the actual y minus the predicted y. Okay. So this point would have a residual of, here is the actual y, 44,961 minus the predicted y, which is 45,387.86. Let's just round the two places there. So if we just go ahead and put that in the calculator, we get negative 426.86. So this data point would be beneath the prediction line. Any point that's beneath the prediction line would have a negative residual. All right, so in this particular graph, okay, it would fall below the prediction line. All right, so that's how we do the algebra on it. Going on to example 9 here. We're moving right along. Says consider the following Minitab output of transformed data. Says the original data was regarding the period of revolution of the planet, so how long it takes to revolve once around the sun measured in Earth years, okay, and their distance from the sun measured in AUs, or astronomical units. Assume the residual plot shows no pattern. Okay, so that's good. That means I can use this stuff. No pattern, that means it's usable. Okay, I can do linear regression on it. Right. Now look at what they tell you here. That's ln of period versus ln of distance. Okay, so that's important to look at. This is the original data was period, but this data is ln of period. All right. Assume the residual plot of the transformed data shows no pattern. So the original data we don't know about. It must not have worked. So they had to transform it. All right, let's do part A. It says, write the equation of the least squares regression line for this transformed data. Okay, well, usually we're used to doing y hat first. Well, this is x right here. Remember, this is the x variable, and that's the y variable right there. All right, so my y variable is period, but it's a prediction, so I need to call it period hat. Okay, equals y-intercept 0.00002544. All right, this is positive slope, so plus 1.49986. All right, times the other variable, but the other variable is a natural log again, so times the ln of the distance. We always put it back in context. So y hat equals a plus bx. Okay, and both the y was transformed to ln of y, and the x was transformed to ln of x. And it says, use your model to predict the period of revolution for Eris, a dwarf planet beyond Pluto that is 102.15 AUs, or that's a distance away from the sun, which is about 9.5 billion miles. Okay, so which number do we use? Do we use the 102.15 or the 9.5 billion miles? We have to go back up to the stem. The distance is measured in astronomical units. Okay, so if I plug that in, if I plug in that value, we get 0.000254 plus 1.49986 times the ln of 102.15. Okay, and if I want to solve for period, remember ln of 102.15 is just going to be a number. All right. How would I get rid of this ln? I would put an e there, which means I would have to put an e there. And that would get that to knock each other out. So I can actually do this in one step. I can go e 0.0002544 plus 1.49986 times the ln of the 102.15. So I can do that in one step in the calculator. Hit enter, and there we go. 1032.02. So that's what the period would be. So if it takes the Earth 1 year to go around the sun, it takes this dwarf planet the equivalent of 1,032 Earth years. Okay, that's how long it would take that planet to go around the sun. So example 10 here says, as more miles are driven in a car, the resale value of the car generally declines. This is called depreciation. For a certain make and model of car, information is gathered on the resale price in dollars and the number of miles driven. Okay, this is the scatter plot of that data. Here's the residual plot of that data. Here's information about the prediction equation and the correlation. Okay. So ask yourself, would you use this model, yes or no? And if you say no, you gotta tell why. Well, when I just look at the scatter plot, data looks kind of linear, right? But the residual, there's a problem. There's a pattern. There's a curved pattern. So I would not use that. Okay, I would not use that one. Okay. Looking at the next one. Looking at the next model for this data. All right, if you take the log, here they're just using a base 10 log instead of a natural log, that's okay. All right, again, data looks kind of linear, maybe a little bit of curve to it. All right, but this is definitely curved. If I look at the residual plot, there's definitely a curve there. Okay, so I probably wouldn't use this model either. Okay. Now, what about if they looked at the x values, or excuse me, the log of the x values versus the y values? Okay. Well, this data looks very linear. Looks almost like it's in a straight line, which is good. And the residual plot shows random scatter. So of these three choices, that's definitely the best one to use. Okay. So in part A, it just says, using model 1, estimate a resale price of this make and model, which has been driven 35,000 miles. Okay. So the predicted price in that case, if I go back to example 1 here. Okay. This was example 1. That's model 1. Predicted price is 29784 minus 343.58 times the number of miles, which is, see, we're only going to put in 35 here, okay, because the miles are given in thousands, so we wouldn't want to put in 35,000. Okay. So if I go ahead and do that in my calculator, 29784 minus 343.58 times 35. Okay. And the predicted price would be 17758.7. All right, part B says model 1 is not the most appropriate to use to compute an estimated resale price. Explain why it's not appropriate and to determine whether model 2 or model 3 is better. Okay. Model 1 not appropriate because the data is not linear, not truly linear. Model 3 is better because the data is linear. And then part C says, using the model you chose in part B, so using model 3, okay, or this model right here, all right, to estimate a resale price for the same car of this make and model has been driven 35,000 miles. Okay. So here we have y hat, or, okay, price, predicted price, that's what the y is. Price is on the y, okay, equals, let's go to the prediction equation, which is right there, 43,254 minus 17153 times the log of the miles, but again, the miles are in thousands. So again, we would just enter 35. And so you just have to be careful by looking at the data. Okay, the original data, the miles were in just, they're already in thousands, so we don't have to add the 3 zeros to the end of that. And so if I type this in, my calculator, 43,254 minus 17,153 log of 35. Predicted price would be 16,768.60. So who does this work out better for? Well, if you're an informed consumer, if you used just the regular old Model 1, plain old linear regression, X versus Y, you're paying $17,758 for that used car. Okay, if you actually understand how the data works and use the best model, you can save yourself about $1,000. Okay, that's why it's important to know this stuff. All right, and that is the end of the notes. So that's how you transform to achieve linearity. All right, not a big topic on the AP exam, but every once in a while they do throw it in there. So hopefully that this video has helped in understanding, and you know what to do and how to do it. So thanks for watching.